Now let's move on to basic hardware design. Physical attacks target the physical implementation of a chip, so this is why hardware design is very important to understand side channel attacks and provide countermeasures for it. So in fact, the attacks specifically exploit the way hardware is built. It is the nature of physical attacks that they target the system as whole with all its details. To understand the attacks, it is necessary to have a basic understanding of a system from transistor to application. So this is why actually cryptography is an interdisciplinary area. You need to know mathematics, computer science, but also electronics. So this part is more related to electronics than actually mathematics or computer science, let's say. So let's talk about synchronous design. The vast majority of IC designs are synchronous designs. So properties of synchronous designs are as follows. There is a state stored in memory elements like registers, RAM, flip-flops. There are combinatorial circuit elements that can do computations. There is a clock signal that triggers to update the memory elements. And synchronous systems are essentially a finite state machine that is triggered by the clock signal. So here's a block diagram of a typical security IC. As you can see, aside from everything, there is a special part for security components. And here you can see that there is a true random number generator. When we were having our synchronous lecture about Proxmark, I show you how to break MyFair Classic 1K smart cards, and I showed you why having a good random number generator is really important. And in the initial versions of MyFair Classic 1K smart cards, the random number generator was faulty, and they updated it. But again, it is very important to have good random number generators. As you can see, there are some co-processors for encryption and decryption and so on. But this picture is not only related to small devices. Even iPhone has internally something like this. It doesn't matter how many cores its ARM processor has. There is also another chip for security, and encryption is performed there. And inside this part, the secret key is stored. So this is why tampering with an iPhone would not give you the secret key that is used for the full disk encryption. So let's look at the development process of hardware. Up to a certain level, the design of digital hardware is very similar to the design of a software. Like in software, abstraction is used to cope with the high complexities of today's systems. During hardware design and manufacturing, there are many levels of abstraction. The design process typically first starts by completely modeling the hardware in software. The high-level model is then continuously refined until there is a description of the design at register transfer level, shortened as RTL. At RTL level, digital hardware is described using a so-called hardware description languages, HDLs, for example, Verilog and VHDL, and so on. At this level, hardware can essentially be viewed as a finite state machine that updates its state in each clock cycle. For each manufacturing technology, typically a library of logic gates is created. Each gate is able to perform basic operations such as NAND, NOR, etc. The synthesis tool maps the functionality described in HDL to the logical gates of the library. The output of the synthesis is a netlist. Essentially, it's simply a graph where each node corresponds to a gate. But to give you a longer definition, let's look at Wikipedia, and it says that in electronic design, a netlist is a description of the connectivity of an electronic circuit. In its simplest form, a netlist consists of a list of the electronic components in a circuit and the list of the nodes they are connected to. Next step is layout. In the next step, the gates are placed and connected. In this step, many physical aspects need to be taken into account. Close placements of gates that are connected, minimization of routing overhead, coupling of wires, and etc. The layout is geometrical description of the design. It describes which material should be placed where. Of course, smaller is better in this scenario for lightweight cryptography, as you can imagine. After the layout has been created, it is sent to the semiconductor fabrication plant. Current technologies for security ICs are 120 nanometers to 65 nanometers. So, and for the wafer sizes, it is 200 nanometers to 300 nanometers. So, the advance of technology in nanotechnology actually gives us better ICs, which requires less power and less area and so on. But again, let's define what a wafer is from Wikipedia. In electronics, a wafer is a thin slice of semiconductor, such as a crystalline silicon, used for the fabrication of integrated circuits and in photovoltaics to manufacture solar cells. The wafer serves as the substrate for microelectronic devices built in and upon the wafer. So after the wafer has been produced, the following steps need to be conducted. Solving, cut the individual ICs out of the wafer. Testing, so no manufacturing process is perfect, hence it is necessary to test each IC. As all the functionality needs to be tested, this essentially means that there is unlimited access to the chip in test mode. It is a serious problem if an attacker can get a chip into test mode. So this is actually a real problem here. Aside from what is written here, think about it in this way. Almost every company now has built their devices in a factory in China, and you don't have much control over the factory. So even if you have a completely safe design and build it there, maybe an attacker might put a backdoor into your design, and you wouldn't know it. Even if you get the device and test it yourself, maybe it will function normally at the beginning, but after some point on, it will function in different behavior. So it is actually a real problem, and you have to even apply side channel analysis to the devices that you built, but in a fabrication plant that you have no or much control over it. So today, this is a very huge problem. And finally, the packaging. The IC is finally packaged and ready to be shipped to the customer, and this is actually what we get at the end.